Hi everyone, welcome to our Metropolis live stream. I'm Debraj, I'm part of the Metropolis product marketing team, and joining me today we have Sammy and Monica, who are part of the product team, and they'll be covering building visual AI agents using our reasoning vision language model Cosmos Reason and our blueprint for video search and summarization. We have a lot of great content to cover, so let's get started. So this is the agenda for today. We'll go over vision language models and VSS very quickly, and then Sammy will cover our notebook where he will show step-by-step process to build a visual AI agent using our VSS blueprint to do summarization and Q&A. And then in the second part, we'll be covering fine-tuning our vision language model. And Monica will be covering how to fine-tune Cosmos Reason with Tau fine-tuning microservice. And we want to keep this session as interactive as possible. So anytime if you have any questions, put them in the chat window. We'll answer them accordingly. So let's get started. So we just want to quickly cover the magnitude of the problem that we're trying to solve here. There are over 2 billion cameras deployed around the world, which generates trillions of hours of videos on a yearly basis. This video data has a lot of information in it, and which can help us to optimize our businesses. To manually go over this video is practically impossible. There's like millions of hours of videos that you have to go through. So the idea is to automate this process. Have an AI agent that can automatically process this video and provide you these critical insights. So that's why only less than 1% of this video is actually analyzed. So we can use this AI agent to analyze millions of hours of videos and help us to get these critical insights. So the idea is to have these AI agents sprinkle around our cities, factories, retail stores, hospitals, airports, which can provide us critical insights from our video data and help us to optimize our operations and make our spaces much more safer. So let me show you a couple of these examples of these AI agents built using our VSS blueprint. So Zach, let's bring up our video here. So yeah, here I want to show you a couple of the AI agents that we have put together using our VSS blueprint. So this is a sports analytics AI agent, and we ask question, which player has the highest chance of scoring a three-pointer? And it answers it correctly. You are a traffic agent. You want to understand what is causing the traffic delay on this freeway right now. Looks like there has been an accident and creates the right report and provides the response team. You are a safety agent. You want to make sure your workers are following the right safety protocols. And here the worker is correctly harnessed and seems like he's following the right safety protocols. You're a manufacturing agent. You want to follow the right assembly steps. So it looks like the worker missed out installing the fan number 3, and it immediately notifies the team so that they can catch it early on in the production process. You're a warehouse agent. You want to make sure everything is working fine. You want to understand the condition of the aisles. Are there any obstructions or spills? So it looks like it generates a report. There's no obstruction or spills going on. Artificial intelligence. Another example I want to show you is that building these AI agents using VSS Blueprint, it not only understands what it sees, it can also understand what it hears. It can transcribe audios as well. So here, Jensen is talking about
has made extraordinary progress
in his keynote.
It has only been 10 years.
And
this is NVIDIA's new DGX, and we call it DGX Spark. 20 CPU cores.
So for example, in his talk, he talks about how many CPU cores are there in DGX Spark, and we immediately get the answer. It's not there in the slides, and he just talks about it. So that's the power of building these AI agents using VSS Blueprint. You're a warehouse agent. You want to make sure there's no unauthorized activity. Looks like a worker without any PP is walking around, so it immediately notifies the security team. You're a facilities agent. You want to pick up on any nuanced activities like tailgating. So these are some of the examples that I wanted to show you where we use this AI agent using our VSS blueprint. So let's go over this pipeline where the AI agent helps us to build these, doing this video analytics at scale. So it can take inputs from archived images and videos. It can also take input from streaming videos. Then the user assigns it a task, like explain what insights the user is looking for. And then the agent can process like vast amount of video data and create a summary. The user can also do Q&A and also create alerts. But to build this blueprint, there are a lot of underlying components there. It uses multiple models like vision language models, computer vision models for tracking, large language model to answer the right questions and build out the answers properly. And then it has also the RAG pipeline, where it has the graph DB and vector DB, so that it can provide the summaries and Q&A. And there are also underlying different services like media management, video ingestion pipeline, all of this put together in the blueprint. So this blueprint provides you the complete software package to build these AI agents at scale, such that you don't have to worry about building these AI agents from scratch. You can leverage this blueprint and get started quickly. And I just wanted to quickly cover the vision language model, which is the heart of these AI agents. So, as you know, vision language models are multimodal models, which has a vision encoder and a large language models. It can process inputs like text, images, and videos. So here we have Cosmos Reason. It is a state-of-the-art reasoning vision language model. It thinks like humans do, using like prior knowledge, physics understanding, and common sense. This model is completely open. You can customize it, you can fine tune it, which will show it shortly. And this is completely commercial ready. You can deploy it for your production environments as well. This model is a 7 billion parameter model, and it is the right size. You can deploy it anywhere from edge to cloud. This model is available right now. We'll provide the links, and you can check it on Build, where you have multiple examples. You can also upload your own video and try it out. And also, you can download in Hugging Face. So this model has been topping leaderboards. It has topped the physical reasoning leaderboard, and we are seeing great traction with our developers. It has over 1.7 million downloads on Hugging Face. Okay, so now I just give you a quick overview of our uh, video search and summarization blueprint. So let me hand it over to Sammy, who will talk about what is there in the blueprint and go over his notebook. Over to you,
Yeah,
Sammy.
yeah, thanks to Braj. So this architecture diagram that's being shown right here, this is the kind of whole blueprint for the video search and summarization agent. And VSS, it's capable of doing Q&A on videos, summarizing long videos, and also generating alerts on incoming live streams or even on video files. And let's kind of walk through this architecture diagram and understand how it's working under the hood. So if we go to the next slide, yeah. So down here on the bottom half, this is the video ingestion pipeline. And this bottom half, at a high level, it's taking in a video file or a camera stream. It's running a series of models to extract all of the most important information, and then it's outputting all of that information into the vector database and the graph databases. And the way this video ingestion pipeline works is as that video file or RTSP or live camera stream is coming in, it's going to get split into a bunch of smaller pieces. So that maybe 1 hour video file will get split into a bunch of smaller 20-second chunks. And this is necessary because the vision language model, it can't take in the entire video file at one time. It needs to have kind of smaller pieces of the video so that it can fit into its context length without a lot of subsampling of the frames from the video file. So we take that video file or that camera live stream, we chunk it into smaller pieces, say 20 or 30 seconds. And then each of those video chunks, the frames and the audio are going to get split from each other. And then that audio is going to go through our Riva automatic speech recognition NIM, and that's going to transcribe the audio from that piece of the video. And then the frames from the video chunk are going to go through a computer vision and tracking pipeline so that all of the kind of objects of interest can be detected and assigned tracking IDs. And then it's also going to go through the vision language model, which could be Cosmos Reason, to create a text description of what it sees in the video. So if you go to the next slide, yeah. So here we can see the output of that video ingestion pipeline. And this is where the combination of all three types of models is being kind of extracted and then put into the vector and graph database. So we have that dense caption coming from the vision language model. So in this case, the vision language model is able to look at this video chunk of the basketball clip, and it's able to write this dense caption describing how the players are moving, what the associated timestamps are, and what the players are attempting to do. And then the computer vision and tracking pipeline, that's going to extract all of the bounding boxes for each of the players, and then also assign certain attributes to them. So in this example, we have um, an OCR model that's picking up on the jersey player numbers, or the jersey numbers for each player. And then the audio transcript is also being extracted from the video. And then all three pieces of information are being combined and sent into the vector and graph database. So if you go to the next slide. So once all of that information is extracted from the video file of the live streaming camera, it gets put into the vector and graph database. And then a large language model is going to be used to kind of traverse these databases and pull out the most relevant pieces of information to either generate your summary, generate an alert, or answer questions about the video. If you go to the next slide. So now let's go ahead and move into a Jupyter Notebook where we can walk through and show how VSS actually works on an example video.
So, Sammy, while you bring up your notebook, let's cover a couple of questions. So we have this question: how do you calculate resources requirements when you know the number of cameras for VSS?
Yeah. So it depends heavily on what models you want to use. So one of the good things about VSS is it really is a blueprint, and it allows you to swap in all types of different models. So depending on the hardware and the number of camera streams that you can support, you can use either larger or smaller models to fit within your target hardware to get kind of the trade-off of performance and accuracy that you need for your use case. So kind of the way you go about sizing is first looking at it from kind of the VLM, because that vision language model is going to be running on all of your video chunks. So your vision language model needs to be able to caption the video chunks fast enough to keep up with the number of live streams or concurrent video files that you want to support. So that's kind of the first step you would need to do to see kind of how many GPUs you need, or to figure out how many live streams you can support for a specific set of GPUs.
Got it. And what are the different VLMs that does VSS support right now?
Yeah, so VSS, it has kind of built-in and optimized support for Cosmos Reason. So Cosmos Reason has been built in directly to the video ingestion pipeline. So that's the most optimal VLM to use within VSS. But VSS can also be configured to call any VLM endpoint that uses the OpenAI API standard. There's a little bit of extra overhead to make those REST API calls compared to using the built-in Cosmos Reason 1 VLM, but it does allow you to use VSS with pretty much any VLM that you can launch through VLLM or SGLang or any other third-party software to run a VLM endpoint.
Okay, one more question before we go to the notebook. Like, can we run it on a single GPU?
Yeah, definitely. So in our product documentation, there's guides for deploying on single GPUs as well.
Perfect. Zach, if you can bring up Sammy's screen for the notebook, that would be great. Thanks.
Okay. So in this Jupyter Notebook, we're showing how to use VSS to summarize a video file. And before I even go into this notebook, let me open up this tab. Whenever you deploy VSS, it's going to allow you to call into a whole bunch of REST API endpoints. And these REST API endpoints, this is your integration point or your way to interface with VSS. So if you're creating your own UI or your own application that needs to take in video files, summarize them, answer questions about them, then this is how you would integrate it with VSS, is by calling these REST API endpoints. And this is what we're going to show how to use in the Jupyter Notebook. So in this Jupyter Notebook, we're first going to start by defining our VSS host. So we're just setting the host name for VSS and the port that it's running at. By default, when you launch VSS, it'll come up at port 8100. And then we're going to have this sample warehouse video file that we'll use. And then we'll import some libraries that we need for the notebook. And we'll skip down a little bit. And like I was just showing, there's a whole bunch of REST API endpoints that we're going to use to interface with VSS. And the first one we're going to start with is the set of files endpoints. So here in the notebook, we're just going to set variables to define each of the endpoints that we'll use. So we'll have that files endpoint, and then we're also going to make use of the summarize endpoint. And then there's also a health check endpoint that we'll use to make sure VSS is up and running. And then a models endpoint that will tell us what VLM VSS is configured for. So we'll start by just running a GET request to that health ready endpoint. And then this will just tell us that VSS is up and running. We got this 200 status code, so that means VSS is good to go, and we can keep going down the notebook. And then next we'll call into that models endpoint, and this will tell us that VSS is configured with Cosmos Reason 1. And later in our summarize requests, this is one of the required parameters. So we're just going to save the VLM into a variable. And we have Cosmos Reason 1. And then this is a specific video file that we're going to summarize over. So let me play this and kind of highlight the important parts of it. So in this video, it's this warehouse scene with several different shelves, and a couple different workers are going to kind of come by and do different activities in this warehouse. So this worker, he was wearing a safety vest and a hard hat. He came by, he accidentally dropped this box right here, and then he's walking off. And then a little bit later, another worker without a hard hat or a safety vest comes by and picks up this box, and he's going to place it back onto the shelf. And then later in the video, this kind of caution area or restricted area is set up. So just kind of indicating that nobody should be entering this aisle. And then another person comes by, they enter that restricted area, and they place this box on the shelf. So as we kind of show some different summarization and Q&A examples, it's good to be familiar with the video that you're using as input so you can make sure that all of the interesting events are being captured. So if we keep going down on this notebook, the first thing we need to do is upload that video file that I just showed to the VSS server. So in Python, we're just going to open it as a binary file, and then we're going to create our request to include the video contents. So we'll set that as the file parameter in our request, and then we're going to add a few extra parameters that VSS requires to tell it that the purpose is vision and that we're uploading a video media type. And then we'll submit a GET request to the files endpoint, and then we'll get a response telling us that we have our video file uploaded. So now that we have our video file uploaded, we can call the summarize endpoint on it, and that will kick off all of the models to start looking at the video, extracting all of that information from it, and then generating a summary that we can read through.
So, Sammy, before we jump into the summary, let's take a couple of questions. I'm seeing a lot of questions coming up on the sampling side of things. So we have this question like, how are the frames sampled for a chunk?
Yeah, so each frame, so by the way I have it configured right now, so there's a parameter you can configure to set the number of frames you want to sample for each video chunk. And the video chunk size is also a configurable parameter. And it's actually here in the body of your summarize requests. You'll set this chunk duration parameter. So here I have it set to 20 seconds. So that means in our 3.5-minute video, it's going to be split into a bunch of 20-second chunks. And then from each 20 seconds, it's going to sample 20 frames. And the number of frames you sample per chunk is a configurable parameter, but I have it set up for 20 per chunk.
And Sammy, is there a minimum and maximum you can do?
Yeah, so it just depends on what your use case is. I mean, the minimum would be 1, and then the maximum would be up to the maximum context length that your VLM supports. So in this case, for Cosmos reason, usually 20, even up to 30. You can also kind of resize the size of your video to have a higher number of frames, but a lower resolution. So there's a lot of configurations you can adjust to increase or decrease the number of frames that are supported.
Got it. So there's another question. Let's say there is a factory floor example. So in case of an 1 hour video of a factory floor, how many chunks would you have to break it into? What are the best practices?
Yeah. So I'd say it depends on how fast the objects in your scenario are moving. So if you have really fast moving objects or you have events that you need to detect that happen very quickly, like a box falling off of a shelf, that event of a box falling off of a shelf is only going to last maybe like half a second. So within that half a second, you need to make sure your frame sampling and your chunk size is going to capture enough frames of that event occurring. So you either need a low chunk size with a lot of frames sampled from it, or a low chunk size with, say, 10 frames sampled from it, or a higher chunk size with more frames sampled from it. But overall, if you look at it in terms of like FPS, like the number of frames you're sampling throughout the entire video, for really fast moving objects, you want closer to like 2 FPS. For slower moving scenarios or objects, 1 FPS or even half of an FPS is okay.
Got it. Sammy, let's take 2 more questions before we move on with the notebook.
Okay.
So is there an integration with DeepStream? And like the video ingestion pipeline is based on DeepStream. Can you talk more about that?
Yeah, so the architecture diagram is also in this notebook, but this is a slightly simpler version of this ingestion pipeline than we showed in the slides, but it captures most of the same information. But this whole data processing or video ingestion part, it's all a DeepStream pipeline. So from the time that this video is coming in and getting decoded, chunked into these smaller pieces, and the frames are getting sampled, all of that is happening in a GPU accelerated pipeline through DeepStream. And then these raw frames are being pushed directly into the VLM running on the GPU. So this whole pipeline, it's very efficient and there's not any kind of unnecessary data transfers or memory copies happening because it's all a part of this kind of really tightly integrated GPU accelerated DeepStream pipeline. This whole data ingestion part is really efficient.
Got it. And so you mentioned that VSS can be deployed on a single GPU. So there's a question, will it be able to run the Cosmos Reason model? Or also have a list of optimized vision models for such deployments on like a single GPU?
Yeah, so you can definitely run Cosmos Reason. So Cosmos Reason is a 7 billion parameter model. And if you have a GPU that supports FP8, then you can run the FP8 version of Cosmos Reason. So that would only use about 7 to 8 gigabytes of video memory. So if you have a single GPU, Cosmos Reason is what we recommend for single GPU deployments.
And Sammy, we can run it on a DJX Spark even on Jetson
Mhm.
Thor and like RTX
Yep.
6000, like on a single GPU. Okay,
Yep.
great. Yeah, let's continue with the notebook. Thanks.
Okay. So let me scroll back down. So we looked at the video, and then we uploaded our video file to VSS. And then after we uploaded that video file, we're going to get back a unique ID for our video file. And this is how we're going to reference which file we want to summarize in our later requests. And then the summarize endpoint is what we're going to call to tell VSS to summarize a video and return that summary to us. And the body of the request for the summarize endpoint, it has a lot of different parameters, and we'll walk through some of them. But the most important ones to point out here are these set of prompts. So there's this prompt parameter, there's a caption summarization prompt, and then a summary aggregation prompt. So these three prompts are really the most important pieces to tune in order to get good summaries out of VSS. And I'll go ahead and run this. These prompts are set up to be pretty generic, and I'll explain how each of these prompts work and kind of how to tune them. So we'll go ahead and submit a post request to the summarize endpoint with the body being this dictionary up here with all of our different parameters to control that summarize request. And now that we've summarized, or now that we've submitted this request, VSS is starting to ingest that video, generate the summaries. So it's calling the VLM, it's calling the LLM, and then it's going to return its response. And then in this content field is that video summary. So let me print it out with this cell. So now here we have it rendered in the notebook, the summary that was returned by VSS. And the summary is pretty short. It captures some of the details. So the main person was wearing a yellow safety vest, black pants, and a yellow hard hat. It missed the box being dropped. It talks about how they were setting up that caution tape and the traffic cones. And then it talks that this other guy came by, put the box on the shelf. So the summary is okay, but it's not really what we want. And that's because these prompts are really important to tune to get good results. And the ones we have in this initial request are just very generic prompts. So let's kind of look at how we can improve those. So to understand how to start tuning these prompts, we need to look at the summarization pipeline a little bit closer. So like I mentioned, the video file that's coming in, it's going to be split into a bunch of smaller chunks. So that video file is going to turn into all of these smaller video chunks. And then each video chunk is going to kind of generate one VLM call. And that VLM call is going to tell the VLM to watch this chunk of the video and then generate a dense caption. So each video chunk is going to have an associated dense caption that's generated by the VLM. So we've kind of taken this video, we've split it up into a bunch of small pieces. We've generated all these captions for each video chunk. And now we need to recombine all of that information to get one cohesive summary. And the way we do that is using the LLM. So for each caption, we're going to group them into batches. And then a batch of dense captions is going to go into a large language model. And it's going to read that batch of dense captions and try to condense it down a little bit and create this aggregated caption. And that's because kind of captions from sequential parts of the video are usually going to have a lot of redundant information. So we have this step here just to help kind of reduce the amount of redundant information from each batch of dense captions. And then once we have all of our aggregated captions, they'll go into one final LLM call to produce the full video summary.
Sammy, while you're explaining the dense caption generation, there's a question for how is the audio handled, and is it multi-language? Can you also talk about the like the speech or like the audio transcription pipeline as well? This one.
Yeah, sure. So at the same time this process is occurring, the video chunks going into the VLM and generating these dense captions, there's also the Riva ASR NIM that can be enabled. And that will also look at each video chunk, or not the video chunk, but the audio from each video chunk and create the audio transcript. And then those audio transcripts are going to get combined with these dense captions so that the LLM has information to both the caption from the VLM and also that audio transcript. So then whenever these aggregated captions in the summary is being produced, it's going to also have that audio information. And the other question is if it was multi-language. I think the one we support out of the box is just English, but there's nothing preventing you from swapping that out with a fine-tuned model for a different language.
Perfect. Thanks, Sammy. Yeah, we can continue with the notebook. Thanks.
Okay. Yeah, so through the series of VLM and LLM calls, we're going to convert our video file into a text summary. And coming back to all of those prompts that I mentioned earlier, each stage in this pipeline is going to have a prompt associated with it, because we have to tell the VLM how we want it to generate these dense captions. And then we have to tell the LLM how we want it to convert these dense captions and create the aggregated caption. And then we have to tell the kind of final LLM call how to take our aggregated captions and format our final summary. So this is why the body of our request up here has really three main prompts in it. It's because we're going through this pipeline where we have to make VLM calls and then also two types of LLM calls. So we have these three prompts here that we need to control. Okay, so the first prompt type is the prompt for the VLM. And usually what works pretty well is to kind of give the VLM a persona and then tell it all the necessary details that it needs to pick up from that video chunk. So in this example, we'll tell the VLM, you're an intelligent warehouse monitoring system. You must monitor and take note of all anomaly or safety-related events in the warehouse, including dropped boxes, PPE usage, like hard hat and safety vest, ladder usage, and any obstructions in the aisles. So one of the most common mistakes that people make when trying to use VSS is they're not specific enough in the prompt to the VLM. Because if you don't tell the VLM what specific details or events to look for, then it's not going to always pick those things up and include it in its caption output. So it's good to be really specific in this prompt exactly what details and events you want the VLM to look for. And then that second prompt, the caption summarization prompt, that's going to the LLM. This one can usually be pretty generic. The LLM, it just needs to read all of the dense captions in a batch and then convert it into a more concise dense caption. So in this one, we'll tell it, you'll be given captions from sequential clips of a video, aggregate captions in this specific format. So it's start time, end time, and then the caption, based on whether captions are related to one another or create a continuous scene. So we're just telling the LLM to take all of the details from its batch of captions and then group it by timestamp, kind of in a list format, followed by the caption itself. And doing it this way will just help timestamp information come through in our final summary. And then the last prompt is the final prompt to the LLM to generate the summary output. So this is where you want to tell the LLM how exactly to format that summary output, and then also reiterate any really important details you want included in the summary. So here we're going to tell it, based on the available information, generate a warehouse safety and anomaly report that is organized chronologically and in logical sections. Give each section a descriptive heading of what occurs in the time range. This should be a concise yet descriptive summary of all the important events. The format should be intuitive and easy for a user to read and understand what happened. Format the output in Markdown so it can be displayed nicely. So you can be really specific on how you want your summary output to be. And here we're telling it to output in Markdown so it can get nicely rendered in the notebook. So now that we've updated those 3 prompts, we're going to submit the same request to VSS, and then we'll kind of see the difference that this makes in our summary output. So while we wait for this request to finish, any other questions, Raj?
Yeah. So, Sammy, one question is that I know you're gonna cover the graph rag and the vector rag part.
Mm-hmm.
So, like this question, you mentioned towards the beginning that some reference to graph and rag was required. Can you elaborate on that?
Mm-hmm. Yeah, definitely. Let me come back to that question. So our second notebook will go into a little bit more detail there.
Perfect. So maybe let's cover this one. Like, do you have any benchmark compared to human beings? Like,
Mm-hmm.
somebody takes how much time to summarize a video, and then
Yeah. Yeah, so we haven't run like an explicit benchmark on that, but for a person to summarize a video, they need to watch the entire video. So if you have a 1 hour video, for example, then a person would need to spend an hour watching that entire video to come up with that summary. But with VSS, for example, if you have it deployed on 8 H100s, it's about 100 times faster than the video length itself. So if you have a 100-minute video, then VSS on 8 H100s can summarize it in about 1 minute. So if you compare that to a human having to spend 100 minutes watching the video, it's a really significant speed up.
got it.
Yeah.
And
Hmm?
just to confirm, like there is a question like it was mentioned before, it can run on a single DGX Spark. So yes,
Hmm.
yes, we have absolutely tried it to run it on a single DGX Spark with Cosmos Reason VLM. So yeah, it's
Hmm.
not just a theory. So yep, you have tried it.
Yeah. 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 And we have a specific user guide just for running VSS on Spark.
Yeah, and we'll also cover like all these notebooks are available. So in fact, you should
Hmm.
see a launchable VSS launchable site. Yeah, you
Yep.
can access this notebook from there. So I'll cover it about it in more detail later. Okay.
Hmm. Yep. So now that our summarization request finished from VSS, we can look at the initial prompts that we provided in the summary response compared to our summary response with the tuned prompts. So with our generic prompts, the summary, it wasn't very interesting. It included some details, but there's no timestamp information. There's no formatting. It missed some of the important events like the dropped box. But after tuning our prompts for each stage of the pipeline to include what specific events we're looking for, and then also all of the formatting details, we're able to get a much more detailed summary. And it's organized in these sections with all of this timestamp information. And then it's able to tell us a lot more specific details. So in this case, it did pick up that the worker was carrying boxes, but one of them slipped from their grasp and fell to the ground. And then later on in the video, uh, one person walks away and then another enters and they come in and they pick up the box and then they kind of drive away in the forklift. It's also able to pick up the shelf labels, so shelves C and D. So Cosmos Reason, it has that OCR capability. It's able to read text within the video. Um, and it's able to get all the kind of most interesting events about the restricted area, the fallen box, the person that comes by and picks it up. So just by tuning these prompts within VSS, you're able to really customize it for your specific use cases. And then before we move on to the second notebook, maybe we can pause for a few more questions.
So there's a couple of questions. Like, is it possible to mask sensitive information to comply with GDPR?
Hmm. Yeah, so I know in VSS, one of the things we have is guardrails. So you can integrate with guardrails to help kind of filter out the input prompts and also the responses from VSS. So with those guardrails, you can tune it to make sure it's not outputting any information you don't want it to output. And that's done through some extra LLM calls that are checking the responses and then kind of reformatting and checking for any details that don't need to go out in the final responses. So that could be one way, but I'm not fully sure on all of the GDPR requirements, so I don't want to speak too much on that one.
Yeah, and another thing, Sammy, I think
Hmm.
VSS itself is a reference application. So
Hmm.
developers can build their more capabilities on top of it. So what we provide is just a
Hmm.
reference app for
Yeah.
them to just get started, and they can build, like, if they want to mask sensitive information or any other computer vision models or more capabilities, they just add on top of it, right? So make it
Hmm.
super simple. Okay,
Yeah.
so and another question is about hallucination. Like, how do we manage
Hmm.
hallucination?
Yeah. So I'd say the best way to manage hallucinations is by tuning your prompts really well, and trying to understand what the VLM is picking up from the video. And then if it's kind of repeatedly saying incorrect things, or sometimes certain details may throw off the VLM, then you can just update your prompts and help the VLM out and tell it, like, what you're looking at is not uh, some specific object. Maybe it's mixing up two types of objects. Then you can just tell it in your prompts, like, this is what this object is. Make sure you don't call it this, or make sure you understand that this object is for this purpose. You can provide a lot of extra background information that the VLM may not know kind of off the bat. So just by tuning these prompts and kind of going through an iterative process to get really good prompts, that's one of the best ways.
So how's the notebook looking? Should we cover more questions or continue with the notebook?
Yeah, so we can continue to part two.
Okay. Maybe we can cover
So,
the graph rag as well, the rag portion. Yep.
mhm,
Perfect.
yeah, yeah. So let's move on to the second notebook that's going to cover how VSS is able to do Q&A. So we mentioned how there's this graph database and this vector database, and an LLM is able to go through the databases and pull out the most important information to answer the user's questions. But let's look a little more closely at how GraphRag actually works, and let's go through an example. So similar to the other notebook, we're just going to define our VSS URL so we can connect to it. We have the same warehouse video that we showed in the first notebook. We're going to use that one again, and then we'll set up the endpoints that we're going to use for VSS. So this time we're also going to make use of this chat completions endpoint. So after you summarize that video file, all the information from that video has been stored in the graph databases. So once that summarize request is complete, then you can make follow-up questions to the chat completions endpoint, and you can reference those previously summarized videos. Okay, so we're just gonna run the cell, check our health endpoint again. It's a success, so we're good to keep going. We'll get that model again, so Cosmos reason 1. We'll save that to a variable, and then we're gonna use the exact same warehouse video. So the worker drops the box. Not really loading, but it's the same video that we used in the previous notebook. And then we're gonna go ahead and re-upload it to VSS. And then we're gonna submit a summarize request again. And in the summarize request, we have kind of our tuned VLM prompts and caption summarization prompt and summary aggregation prompts. So this is pretty much all the same as the previous notebook. And then the new part is going to be using this chat completions endpoint. So we'll wait a few seconds for this video to get ingested. And then while that's happening, I'll go ahead and explain this function. So we're just writing a simple wrapper function around this chat completions endpoint. So to submit a query to a video through VSS, the payload is pretty simple. You give it an ID of the video that you uploaded. So that video ID is coming from up here. After we uploaded our video file, we get that ID back. And then in our messages parameter, we're going to have this content field and then our query. So this query, this is your question that you want to ask to VSS about the video. And then we have to include the configured VLM. So this function, it just helps us call that chat completions endpoint and then parse the output to get the response. So now that the summarize request has complete, that video file has been fully ingested, and then we can ask questions about it. So we can call this function and we can ask things like, skip the cell, like, was there a forklift? And then VSS is able to tell us, yes, there was a forklift. And then we can ask, was a worker carrying the box wearing PPE? And then it's able to say, yes, the worker was wearing a yellow helmet and a yellow safety vest. So how is this actually working? How is Q&A able to actually function like this? So kind of what's happening is as all of that metadata and information is coming out of the computer vision and ingestion pipeline, we're getting those dense captions from the VLM, and then also the audio transcripts, and then any detection and tracking data. And all of that is going into this graph extraction and indexing process. And this process, it's taking those dense captions and then figuring out how to convert it into a kind of subgraph to insert into our graph database. And that subgraph, it's going to be a set of nodes and edges that is capturing the relationship between objects and different events in the video. And I'll show an example of kind of what that looks like in a second. But we're going to extract all of these nodes and edges from each caption coming out of that ingestion pipeline, and they're going to be stored into the graph database. So then whenever we get a user query, this graph retriever process, it's going to be using an LLM under the hood, and it's able to call into this graph database and traverse those nodes and edges to get the most relevant information. And then it's able to compare that information with our question and then formulate the final response. So that graph extraction process, kind of one example, if you have a caption coming from the VLM, like a worker places a heavy box on the conveyor belt and the box falls due to improper placement, then a large language model is going to inspect this caption and then figure out how to convert it to those nodes and edges. So in this case, the nodes could be the worker, the box, and the conveyor belt. And then it can also assign it kind of a specific category or specific properties to go along with the nodes. And then the relationships between these nodes could be worker places box on conveyor belt or box falls due to improper placement. So we're kind of extracting the main objects from this caption as the nodes, and then the events or the relationships between those objects are being captured in the relationships or the edges connecting those nodes.
So, Sammy, one quick question on that. How are there's a question on how our graph keywords are selected to build the graph.
Yeah. So it's all done by the LLM. So there are some kind of internal prompts that you can configure to specify kind of what types of nodes you want to restrict the LLM to trying to extract. But by default, the LLM will try to come up with what nodes are most important. And that's purely based on the captions that is being provided. So it's kind of the power of the LLM that's able to figure out what nodes need to come out of these captions.
Perfect.
Hmm.
Okay.
And then, so once all these nodes and edges are extracted and they're put into that graph database, the graph database can then be kind of traversed and information can be extracted from it. So the LLM is going to figure out, based on the user's question, what type of query it needs to perform on the graph database to extract the right information. And one of the new features in VSS 2.4 is chain of thought retrieval, where the LLM can go through an iterative process where it gets relevant information, it checks it against the user's question, and then determines, does this information actually answer the user's question? If it doesn't, then it will adjust itself and go back and pull more information from the graph database and then try again. And it will do this in an iterative manner until it has high confidence that it's answered the user's questions correctly. And then let me skip down to this diagram because I think this will make a lot more sense to have a visual of what this graph actually looks like. So from that warehouse video, after we generate this graph, it's been through that video ingestion process. All those captions have been inspected by an LLM, and that LLM has figured out what all these nodes and edges should be, and then it's inserted it into the graph database. And then this is kind of the full knowledge graph that we get from the warehouse video. So it includes a lot of interesting, I guess it might be a little, might not zoom in too much here, but you can see some nodes, like there's this worker node, and he's interacting with like section D, so that's that aisle D shelf, and the relationship between these two nodes is walk towards. So you can see how this graph is able to capture kind of the important objects and how they're interacting with each other throughout the video.
And Sammy, what frameworks are we using for these graph rag, vector rag?
Yeah, so for GraphRag, there's support for a couple different graph databases. You can use Neo4j or ArangoDB. And this is also using LangChain under the hood to do some of this tool calling for the LLM to interface with the graph databases.
Great.
Yeah, and then we can ask a few more questions. So what could be some possible safety issues in this warehouse? When did the forklift appear? Describe the warehouse setting in detail. And for each of these questions, the LLM is taking that question, it's figuring out what are the most relevant nodes and edges in the graph database, it's retrieving that information, and then it's formulating its final response to answer the user's question. And once we're in this Q&A process, you don't have to re-ingest the video again. Since everything is stored in these graph databases, the Q&A is pretty fast because it's just a couple of LLM calls that are occurring under the hood to retrieve the information and answer the question. So once you've done that summarize request to ingest and process a video, these follow-up Q&A questions are pretty low latency and very fast. And that's the end of the second notebook. So Debraj, are there any other questions we want to answer to wrap up this part?
I think let's go over to the second part of this session.
Sounds
but
good.
Sammy, this notebook was awesome. There were a lot of questions and people want to try it out. So yeah, thanks for sharing it. So now let's go back to our slide and we'll have Monica talk about vision language fine tuning. So if you use the vision language as is or just right out of the box, you might get some okay accuracy for your use cases. But to get to the right, like great accuracy, you have to absolutely fine tune the vision language model. So here, let me hand it over to Monica.
Thank you, Debraj. So, like we discussed in VSS2, the CV, the Cosmos region is the VLM model that we are using in our blueprint. And if we take a look at this particular video, you can see we are just trying to see, like, there's a collision in this, and there are two cars. Those are involved in this collision is the black car and the white car. And with the base, the brush, can we go back to the and if we look at the base model, Cosmos Reason 7B model with zero shot, and you're asking a question like if there is any car collision in this video, and if there is any, then describe which vehicles are collided. With zero shot, you can see the reasoning trace of the CR Cosmos Reason model, and you can see like there are a couple of information that it does really good out of the box with zero shot. For example, there's a black sedan car, the left side or the right side. So the model is really good at understanding the special information and locating the object, but it doesn't really understand the definition of the collision. So for these type of scenarios, what we did, we took like a few the traffic, smart traffic safety related videos. We fine tune our CR model, and at the right side, the fine tuned result looks like now the model is able to understand what exactly the collision is. And if you look at the reasoning traces of it, it does a pretty good job in defining the definition of collision, when does it occur, and in between what type of the object. And there's a couple of the small tricks like the red car. These are the type of thing after the fine tuning. If you still look at it, then that means like in your data set, you probably want to augment your data set that has more of the vehicle attribute to it, or the images that need more of the red car type of videos as well. So, if you look at the entire lifespan of VLM, it starts with and the fine tuning of the VLM. We start with filtering some data set. Those are useful for the use case that you are picking it up, and then define if with that new use case, if the base CR model itself is not working well, then we go with the entire fine tuning pipeline. And for that, we do data annotation. For example, in this scenario, you can have the Q&A, what type of the questions that you're interested in most. And then those augmented labels data set, we feed it into the model fine tuning, and that the fine tune model, once that fine tuning is done, you can deploy it using just the Cosmos Reason NIM, or you can deploy it within the VSS. And there is for optimization, you can use FP8 quantization that we provide out of the box. So, in this session, we're going to talk about Cosmos fine-tuning with Tau microservices. What it does, Tau microservices, the train adapt fine-tuning microservice. You can run it on like a workstation. You can run it on your on-premise. You can run it on cloud. All you need to do, it tries to wrap the entire thing, the fine tuning, abstract away the entire fine tuning in such a way that you don't need to know like nitty gritty of like what exact the fine tuning parameter that I need to know, that I need to tweak to get the best accuracy out of this model for the defined use cases that I picked. You are providing the base model, which is like in this case Cosmos Reason 1, and you are providing your training data set. This microservices kind of scalable. It provides you a scalable deployment, and it has the unified APIs, and it also has an NVIDIA support. And we do for all the to get the best accuracy out of the fine tuning exercise, we support AutoML into it. So if you look at this particular graph, the gray graph is to showcase the best accuracy by the developer, meaning a developer who knows everything about how to fine tune a VLM, and they are able to tweak each and every fine tuning parameter. With that, you can get like about for one of the use cases, one of the data set that we talk later, with the traffic understanding, 89.2% of accuracy. But if you enable the AutoML, you don't need to know like all the parameters, all the hyperparameters. Those are needed to fine tune your model, and you can get the accuracy like 91.5. And just to mention, the gray is kind of the developer who are working in the CR like day in and out. So you can see the use of the AutoML is kind of exceeding all the manual effort that you might gonna put on putting together these hyperparameters. For this different kind of the use case that we have in our Cosmos cookbook, there's a warehouse spatial understanding use case or the case study, and there we see like a great 4% of increase in the accuracy with AutoML. So, to get started with Cosmos Cookbook, we do provide a couple of out of the box cookbook for the two different use cases so far, and we tend to extend it. And these two use cases are, one is for the outdoor safety, which is the intelligent traffic system. Another is a warehouse case study, and for that you can click on any of this link, or you can go to the Cosmos cookbook, and you should be able to see in more detail on each of the use cases. And later in the session, we will take the first use case, which is the traffic scenario, and we will go through the different steps those are needed to fine tune Cosmos Region 1 using Tau FTMS. So yeah, with that, let's get started with the notebook.
So, while Monica, you're bringing up the notebook, maybe there's one question on Cosmos Reason. How does Cosmos Reason differ from the Cosmos World Foundation models? So it actually doesn't. Cosmos World Foundation models comprise of three models: predict, transfer, and reason. So yeah, so it is part of the Cosmos platform. So you can check it out. You can just search Cosmos NVIDIA and just see the three models that are there.
Okay. Yeah. So yeah, so this is the notebook, and the showcase the entire fine tuning steps that those are needed to fine tune Cosmos Region 1. You can also find this notebook on our Tau FTMS GitHub repo. And to get started, like we discussed, we're going to use the Tau FTMS microservice. There we have a base model as a Cosmos Reason model that we're going to pull in into the Tau FTMS. And the training data set, that is something for this scenario, we're going to use the traffic data set that we discussed before. And we are running it on we are running it on 8A100 server. And just to get started, the first part is to go with this particular sample video. And if you look at this particular video, there are a couple of people who are walking into on this crosswalk, and somehow this is kind of getting stuck at. Um, Somehow this, okay, I can say. So there are like two person who are crossing the road, and if you ask this question, like describe the first two pedestrian in the video, the base model answer is like the woman is wearing the purple top and black pants, and the man wearing a red shirt and blue jeans walk across the crosswalk. But the real answer is the person who is behind the another person is kind of occluded. So we'll see after fine tuning if we are able to improve the answer, and if we are able to improve our overall accuracy for the particular the data set that we're gonna pick up. So just to get started with our FTMS, there's in this particular section we talk about what is the minimum hardware needed, and you can and there's a good amount of documentation available on our Tau FTMS developer page. There you can go and check for like what is the minimum requirement, what are the different method that we support. You can use it either a Kubernetes server, or you can use Docker Compose just to deploy your FTMS. After that, once you follow these steps, you should be able to deploy FTMS. And after that, we just gonna set up a couple of configuration parameters just to get started with the fine tuning. And one of that is the setting up the host URL. So that you can do different kind of the API call, DAO API call. Then NGC key, we have our model and the Cosmos region container available on NGC Cloud Registry. So you need to provide the NGC key, or if you don't have one, there's a documentation in the DAO FTMS documentation that you can take a look at and generate the NGC key. Hugging Face token, just to pull the base Cosmos region model. So after setting like these different configuration, we are making sure that we have the fine-tuning microservice up and running, and you have the host URL just to call each and every APIs, and you're setting the model name for which model you want to do the fine-tuning. In this case, it's a Cosmos region. So we're gonna pull the base model for Cosmos region, which is latest on the HF, right? Anything related to AutoML configuration, you can set it up. And after that is done, and you're done with the setting your host URL and all this configuration, we're gonna log into the host. While logging into the host, we can kind of create a JSON web token, JWT token, and the meaning of it is like you bring up all your configuration. For example, your Hugging Face token, your NGC keys, or any different kind of the cloud keys. And at the entrance, you are basically getting a badge, a temporary badge, which is your JWT key, and that is required to do each and every Tau API call. So if you click on it, it will basically click, I'm gonna create a JWT token. And for the entire fine-tuning experiment, we're gonna pass this token so that we can do the each and every Tau API call for the training, for evaluation, for inferencing, and so more. Given that this fine-tuning microservices designed in a way that you can use your you can pull your data set from any of the cloud or even from the local repository. And for that, like any of the cloud related configuration, if you have to set, for example, you might have your data set in AWS, or it might be somewhere on your local. And so you probably have to just add all these credentials. And after that, you can pull all your data sets. So in my case, like I have my data set on AWS, and the name of the space that I have is in the Tau workspace. So dataset preparation. In this case, we are using like this particular data, WTS woven traffic safety dataset. It has about 1.2K videos, and each video is about 70 seconds long. And we are taking almost half of this, even the 1/4 of these videos, just for this experiment, and to showcase like how exactly the accuracy looks like before and after. And the type of question that this particular data set has is kind of the VQA, or the multi-choice questions. And in this, the data format is kind of the key, because in FTMS, out of the box, we support Lava format. And the meaning of Lava format is you have your labels in this particular format, where you have the human key and the GPT key. In the human key, you are kind of asking your question, and in the GPT key, you have your answer. And there can be like different categories into it, like distance, or MCQ type of question, or the VQA type of question, or the normalized answer, which is like single string answer, or the free form answer is kind of the multiple sentences of the single sentence. The reason this thing matters, because at the evaluation or at the fine tuning, you want to make sure your model understand the long sentences plus the smaller sentences. And the evaluation, when we are doing the evaluation, there are multiple evaluation matrices in VLM. But in this notebook, we are trying to make sure the evaluation that we do is on the top of the normalized answer. That means in your fine-tuned model, what are the response that you get? If that string matches 100% to your normalized answer, we give them score as like 100% score for that particular query. And both for that particular video, the model was able to get the 100% accuracy for that scenario. So next, if you just as a housekeeping, you have your data set, where exactly that data set is in the cloud repository. For example, in my case, I have this data at this particular path. So you just have to define where your trained data set and the eval data set is. Now, for the dataset format, like we discussed, there's a Lava format. That is something we support out of the box. And the meaning of that is, as long as you have your data in this particular format, you don't have to deal with how to tokenize these different tokens, like where your question token is, where your answer token is, or if there is any kind of the separate metadata, like we discussed before. Example, the normalized answer, the categories, or the free form, or any of this, that is supported out of the box. As long as you have your data in the Lava format, you define this format as the data loader that I want to pull in for this fine tuning should understand the Lava format. So after that, you can go through this particular cell, which is about pull your trained data set from the cloud. And for that, we're gonna use the we're going to fill our metadata with the what kind of the data format that you have, which workspace ID. The meaning of workspace ID is like at the initial at the beginning of your fine tuning exercise with the FTMS, we define a workspace ID. That workspace ID stores all your intermediate checkpoints, all the logs in between, all the data information, everything that is needed to complete your finding from start to end. And this ID is the point which you can talk about. Okay, I did this fine tuning 2 days back, and my workspace ID was this, and that is where I can find all the information related to this fine tuning. So similarly, what train data set path that you want to use for this particular fine tuning, you can define in this metadata. After this is done, you can use this metadata and use the endpoint dataset API, and it will pull your cloud data to local. And similarly, just to know, check the download progress. If the download is done, you'll see the status as complete. Similarly, as the
So,
training.
Monica, let's seeing a lot of questions coming in. Let's take a couple of them. Okay,
Mhm.
is that fine? Before we continue with the notebook.
Yeah.
So, regarding the data annotated training data set, like how is the labeling and annotating proceed? Like how it's done?
Yeah, so for most of our data set that we have generated and labeled, we do provide all those labels, and we do provide a couple of labeling recipe as well. For example, there is a special AI warehouse data set that we have a labeling script that talks about how exactly we label that data set. And that detail, you can find it on our Hugging Face open source data set. And there are like GitHub repos related to any of the VLM fine tuning that we do within NVIDIA. Each and every repo talks about how did we label the data. For example, if you have like if you're creating a special warehouse data set, you might be interested where each object is, how far these objects are. And for that, we used a different kind of the CV model, or if you're using Isaac sim within to generate the synthetic data set, there are out of box labels. Those are generated. We use those CV labels, and we augment those CV labels to generate Q&A pair for the VLM.
Correct. And just to tell the audience that this Cosmos Reason fine tuning notebook is available, so do check it out here. And Monica, in terms of the GPU that one should use, like how does it matter? Like, is it the amount of training data set that you have? Like how, like any
Yeah.
suggestion there?
Yeah, so on the GPU, for example, we do mention like you should, for the Cosmos region fine tuning, you should minimum have like four A100. But in CR, the fine tuning that we have, we do support multiple parallelism for the optimized training. And the minimalistic that you can run at like 30 gigs of memory with eight such GPUs. That is the minimum requirement for the Cosmos region. But all the experiment that we have done, just to reach to the same accuracy, you should have like at least minimum to eight A100, or if the yeah, if you want to like map how much time the training takes. If the data set doesn't change much, in the sense like the data set is large or small, but to load the entire parameter into the GPU memory, you need to have that much minimum GPU at your hand.
Got it. Got it. Okay. Thanks, Monica. Yeah, we can continue with the notebook. Thanks.
Okay. So once okay, so here we talk about the initial two part, the configuration, and anything that anywhere you have to pull your data set. Once the data set is kind of ready, the training data set and the evaluation data set, you can look at like what all data set do I have for this particular workspace ID, which means like in this experiment, I'm going to use these two data set ID. One is for the training, another is for the evaluation. For the experiment in this particular FTMS microservices, like we support chain multiple model action together. What does that mean? Is like you are doing the training at first, and after training is done, you want to pick the best model that was fine tuned with the training, and you want to do the evaluation with that particular model. Without this chaining, you have to manually go to, like, I need to pick this particular fine-tuned model and I want to do my evaluation, or I need to start my fine-tuning from that particular point, and then I need to decide like which was the intermediate checkpoint that I should pick it up, right? So all that is kind of a little bit hidden or abstracted away in FTMS. And you can define, I need to do like these set of the training evaluation in one of the chain. And once you start your experiment, which is you create your workspace ID, which is your experiment ID in this scenario, and the network architecture, which is like which model that you are looking for, that you're going to get started with. And after once you click this particular one, you can see there's an ID that is created. This is your experiment ID, and that stays for the rest of, or for the remaining of your experiments. And then it has some kind of the metadata that talks about what kind of the data set format did you pick at the beginning, which is lava, and what kind of the chaining that you want to do, which is the training and evaluation. And if there is any kind of the data set that you are using, you can it does list out like what kind of the data set that you're using, and what kind of the checkpoint choose method, which is like best model, meaning at the end of your training, the best trained model you're gonna evaluate it against. So in my scenario, I was running a couple of experiments. And so if you run this one, this cell, it talks about the all the experiment. It does list out like if you have a couple of experiment and for a couple of days, it does list out like what all these experiments are, when did you start it, and what kind of the model architecture does each experiment belongs to. For example, in this case, this is a particular ID, and it belongs to the Cosmos reason fine-tuning network architecture that I was doing this experiment on. So after that, we assign the train and evaluation data set, which is like I have this experiment ID. I just want to map my training data set and the evaluation data set, so that all the training and evaluations are done with this particular with these multiple data set as well. So for this training, you can we're not going to go with the entire training because it takes a couple of hours to complete, but we'll click on a couple of cells just to see. I have a checkpoint that I trained a few hours back, and we're going to use that particular checkpoint, and we're going to see the accuracy of this model that maps to what we saw in the PPT initially. For the configuration, for the training configuration, like I mentioned before, we use AutoML, and it's completely up to you. You can turn it on, you can turn it off. But I wanted to highlight like what all hyperparameters do we include in the AutoML. For example, all of these hyperparameters are actually tweaked with the AutoML, and there are multiple different AutoML algorithm that we support in FTMS. Like Bayesian is one, and you can in this experiment by default I'm using the Bayesian. But if the user is not writing any of these config parameter, for example, if you're using the LoRa rank, something if you haven't come up with, the AutoML will make sure like this is done. This is selected in a way that it is optimal for your data set, and it is optimal to get you the highest accuracy. Similarly, for the learning rate and for the vision FPS or the different configuration parameter that we support out of the box with AutoML, these all parameters will get filled if you choose to use the AutoML in it. There's a good amount of documentation if you look at this particular notebook, and you can find out like what each hyperparameter is for what. And then the next is if you have to like tweak, for example, for each and every default hyperparameter configuration, whenever you select which network architecture you're going to go with, in this scenario, Cosmos region is one, then all these base hyperparameter, we make sure like those are relevant to that particular model. They are not randomly picked. Those are picked by we have kind of crafted those so that AutoML starts from that base configuration, and then you get like higher accuracy on top of it. So for that, but anybody who wants to like change any of this configuration or tweak any of the configuration, it's very much dynamic. You can look for like these are the different parameters that model going to accept, and in this cell, if you want to update your experiment metadata with any of it, you can definitely the cell below talks about the different configuration yeah, for example, the AutoML algorithm, if you want to choose the Bayesian, or if you want to use AutoML enabled or disabled, or if there is any kind of the hyperparameter that you want to choose, you can just change each and every parameter too. After this, the wording in the action in the FTMS is kind of like which particular action that you want to start. Training is like one of the action, evaluation is one type of the action. And then we create a job map, and that job map will keep on extending on the basis of like what all training action that you have included in your experiment, right? So we start with there are different kind of the for each action, we have like different kind of the APIs that you can get started with, which is like, if you want to define any kind of the defaults, in each and every API, you can change the different default configurations. Then you can also have the monitor the job of it, like for example, once you're running the training, you can also look at like what my training looks like, how many epochs are done, and if the training is done, when it was how much time did it take, right? So after that, get default spec schema, which is like these are the different spec whatever we discussed initially, and you can list down like what all different training schema that it needs, and you can go for like different experiment name related to the training configuration, and also like what kind of the different policies that we enabled, right? Customized train model configuration. So for example, you have a smaller GPU like we were discussing before, and you want to fine tune the Cosmos region. And in the Cosmos RL, there is a fine tuning container that runs behind the FTMS, supports like multiple different kind of the parallelism, and few of these are like this. We support FSTP, for example. DB shard size is the key. If you enable it, you can enable the FSTP in that. And the if let's say you're running on the instead of 80 gigs of GPU, you're running on the 40 gigs of GPU each. You can increase the DP shard to the number of GPUs that you have, and you can maybe increase. There's the different kind of the optimization, like the tensor parallelism and the pipeline parallelism that we support out of the box in the Cosmos RL. Anything that you need to update in these training spec before you trigger the training. And if you see like your platform can support these many number of this much of the VIT maximum pixels, or this is the DP shard number of GPUs that you have, or the model max length that you want to set. So these all configuration you can set it before triggering the fine tuning.
So,
Devashri?
yeah, wanting a quick note. So we are going over. So can we just cover the most important part?
Yeah.
And we have provided the link for the fine tuning.
Mm-hmm.
So let's probably we should start wrapping it up right now.
Okay, sounds good.
Sure.
Yeah.
Thanks.
Yeah, so I think we already provided the link for this particular notebook, and you can go through each and every cell. I just wanted to like quickly jump to the evaluation. Uh, and in this evaluation, I was running this evaluation before, and I have this particular checkpoint at AWS S3 bucket, and I this is the checkpoint after fine tuning that I got. And once I run this particular evaluation for this WTS data set, you can see the initial accuracy was about 41% for WTS, and after the evaluation is kind of done, you can see the accuracy is about 92.993%. So this is just to showcase this one of the experiment. If you want to know what we did in detail about this WTS data set, you should definitely look at our cookbook that talks about all the different kind of parameters, all the different kind of the tweaking that we did to get or to reach to this particular accuracy number. And after that, once you're done with the fine tuning, you can clean up all the training data set, all the validation data set. And for the inference, we do support like inference microservice. And with that, if I'll just quickly go to the cell which I was running. So for the same video that we looked at the beginning, after fine tuning with this particular fine tune checkpoint, it does talk about a little bit more about the person, and then what kind of the attribute the person is holding, and about a little bit information about the other person that was occluded with the person in the purple jacket. So yeah, for each and every microservice, you can stop the microservice, and for the model deployment, the model deployment for the Cosmos region after you're done with the fine tuning is via NIM. You can create the NIM out of your fine tune checkpoint, and you can deploy it within VSS or a standalone Cosmos region NIM microservice. Yeah, that's pretty much it.
Perfect. Thanks, Monica. Yeah, thanks for sharing the notebook. That was super helpful. So just to wrap it up, what are the next steps? The first thing is to get started with the VSS blueprint. We have made this process super simple for our developers to get started with VSS. First, just check it on our build site. There are multiple examples that are provided for VSS. You can try it summary, Q&A as well. So now if you want to quickly try it, so we have the service called Launchable, which is a sandbox environment where VSS is already pre-deployed. So this is like GPUs are available in the cloud that you can try it out. So right now, the QR code that you're seeing here, so we are giving like a limited time offer, some free cloud GPU credits. You can just scan it, go to the Launchable link there, and you can try it out. So this is limited and first come first serve basis. So just quickly deploy it on our Launchable, and you can try out VSS over there. So now if you want to deploy it on your own, like on-prem hardware or public cloud, you have the option to download VSS as well. You can use the link from a build site, and the notebook that Monica was talking about, the VLM fine-tuning microservice, is also available in that link. And then finally, to deploy VSS to production environment, you can use our NIMs. So yeah, so we covered building visual AI agent using our VSS blueprint and Cosmos reason, and also we showed you how to fine-tune the vision language model. I hope this was super useful for you. Thank you so much for joining. We really appreciate it. Have a great day. Thank you so much. Take care.